All right, welcome back, everyone. Our next speaker is Anne-Marie Aubert from the Institut de Mathématiques de Jussieu, Paris, and CNRS. Right, Anne-Marie, thank you. And the screen is yours.
Okay, thank you very much for giving me the opportunity to talk at this summer school. So I will talk about periodic representation of periodic groups. So I will try to emphasize the difference and the analogy with real Lie groups. And first, so today it will be basic notions, and next lecture will be more about temporal representation, and the last lecture I hope to go to K-theory. So first, some fact about the field we are interested in. So periodic field. So what is a periodic field? It is a finite extension of a field of periodic numbers. So there is two ways to complete the field of rational numbers Q with respect. One is with respect to the usual absolute value, and the other way is, and in that case you get the field of real numbers. And then if you take a fixed prime number P, you can complete Q with respect to the so-called periodic absolute value, and in that case, we get the field QP of periodic numbers. So what is the periodic absolute value? So we can define it as follows. So first, when we have an integer, you denote by O Pn the exponent of P in the factorization of that integer as a product of prime numbers. Then the periodic absolute value is defined just by, if you have a rational number, A, can be written as A mod B. You just take P at with the exponent, the order of P of B minus the P of A. This is when the A and B are non-zero, and for 0, we just take 0. And when you do that, you can consider an interest, define a ring which is attached to QP. In fact, QP is the fraction field of that ring ZP. And ZP is defined as the element in QP which have no periodic norms less than 1, less or equal to 1. Sorry. And the periodic field will be for us a finite extension of QP. So I said for us because in fact periodic field is a local field as R, but it is a local non-Archimedean field, and there is other, and it has zero characteristic, and there are other kind of non-Archimedean local fields, which are obtained by taking finite extension of a field of formal series Fp of T. But we will not consider, and this one have characteristic P. So we will not consider this case here. It's essentially to simplify because some results are known and only in the case where the field has zero characteristic. So and similarly we can define. We can extend in a unique way the periodic absolute value into an absolute value over F. And it satisfies what is called the ultrametric inequality, which is the following. So the norm of x plus y is less or equal to the max of norm of x and norm of y for any element x and y in the field. So similarly as for QP, we can define a ring of integers of f as it is written here. So it is essentially the same definition. And this ring will be very important for us. So it is a local ring, and which means that it has a unique maximal ideal, and the ideal PF is the set of elements in F which has a norm strictly less than 1, and generator of and this ideal is principal, and it has a generator which we can, and that generator can be is called a uniformizer of a field F. So the interesting thing is that when you consider the quotient of OF by PF, you get a finite field and of characteristic P, which is called the residual characteristic of F, and we denote its coordinality by Q, which is a power of P. And the unit in OF define a group, and we have the elements which are norm exactly equal to 1. And then you can you have the following things. You can view your ring as the projective limit of the quotient of OF modes the power of PF, where M is greater or equal to 1. So now we can define p-adic reductive group as the group of rational points of sorry, I'm playing with my iPad. Excuse me. So here it is. So a p-adic reductive group is the group of a F rational point of a connected reductive algebraic group that are denoted by blackboard G, which is defined over F. And for the rest of the lectures, we will assume for simplicity that group G is F split. So it is a special, so it has an interesting structure. So it is a locally profinite group. So we'll go to this now. So topology group is set profinite if it is compact and totally disconnected, which means that any connected subset of G is a singleton. And as an example, we can take a finite group with discrete topology. And we can characterize profinite group by the existence of a topological isomorphism with the limit of G mod n, where n runs over all the open normal subgroup of G. So it is a projective limit of a system of finite groups. So we just give a name profinite. And conversely, such a projective limit is a compact and totally disconnected group. So it is profinite. So p-adic reductive group are not necessarily profinite in general. So but we are locally profinite, which is the definition which is here, which means that they satisfy one of the following equivalent conditions. So the group is locally compact and totally disconnected, and this condition is equivalent to the following, which is the one which is usually used to in many proofs, is the fact that every neighborhood of the identity in G contains a compact open subgroup. So this is very different from what we have for real groups. If we take a group which is locally profinite and also compact, then it is profinite. So we will see now two typical examples of locally profinite group. So first, when you have QP, you can consider its additive group, and it is a locally profinite, and it's easy to find a fundamental system of neighborhood of 0, just given by you take the power of okay, so this P should be, yeah, it's for QP, sorry. It's the power of P, there is no F, yeah. And okay, so it's the, you take the power of the prime order P times ZP. And similarly, for periodic field F, you take the fractional ideal PF at the power M, where M is an integer. And then this gives us a family of compact open subgroup, and F is the union of this fractional ideals. So this is the first example. The second example, which is actually the most interesting for us, is taking now the multiplicative group of F, and here the system of neighborhood of the unity 1 is given by the open compact subgroup 1 plus PF at the power n. And all these compact open subgroup are contained in the unique maximal compact subgroup of F cross, which is OF cross. So this is a special interesting example because you can, of course, view the F cross as GL1 over F by definition. So, and so it's this can be extended to GLN over F, which are invertible matrices, n by n matrices with coefficient in F. And this is the first example of p-adic reductive group that we can consider. And of course, another example that will interest us would be SL2 over F. So several properties of a representation of a p-adic reductive group can be already stated in the more general context of locally profiled group. And notably, the definition of a smooth representation, which will be very important for us, and it is the following. So you start with a representation V, a pi, sorry, with carrier space V, and it is said to be smooth if for any vector in V, the stabilizer of V is an open subgroup of G. And a representation is admissible if for every compact open subgroup K of G, the dimension of the fixed vectors of V, which are invariant by, which are the vector of V, which are invariant by K, is finite. So it is an important result is that if you only consider irreducible representation, then these two notions coincide. So every irreducible smooth representation is admissible. So now I will finally come to the subject of a lecture. So p-adic reductive group. So we start with F, a p-adic field, and G, blackboard G, a connected reductive group defined over F. And we denote by G the group of F rational point of G, and we will call it this G p-adic reductive group. So examples, as I already mentioned, you have GLNF, SLNF, P projective linear group. So you take the quotient of GLNF by its center, and example of classical groups. So GLN is a classical groups, but also symplectic or special orthogonal groups. These ones are connected. You might also consider orthogonal group, but it will not be connected, and so it will not enter in our list here. And also groups of exceptional type. One thing is that, general thing is that you can always consider the group of, so it should be bold G here. And so G over OF is a maximal open compact subgroup of G. So in the case of GLN, all the maximal open compact of GLN are conjugated in GLN with this group, with GLN over O. but it's not always the case for other groups. And for instance, even for SL2, you will have two conjugacy classes of maximal compact subgroups. So one will be SL2 over OF, and we will have another one which is conjugating with SL2 over OF in GL2, but not in SL2. So we'll come back to this later. So another notion which will be useful for us is the notion of contragradient of a representation. So to more precisely, when you start with a representation pi v of G, you can, which is not necessarily, which is not assumed to be smooth, you can attach to it a smooth representation just by taking the element V of a vector space V, which have open stabilizer. And you can consider the dual of V, so V star, and for any linear form of V, so element in any lambda in V star and any element V of V, you can consider the value of lambda on V and define a representation we can view as the dual of pi with space V star, which is defined which is defined here. And so it is a representation, but the point is that it is not necessarily smooth. And so you're interested in a smooth part. So you will consider the representation pi tilde, which is the sub-representation of V star, taken by defined by taking the smooth vector of V star. So this representation is called the contragradient representation of pi. And in the case where pi is admissible, if you take the contragradient of a contragradient, you recover a representation which is equivalent to the original representation pi. Also, when we have an irreducible smooth representation of G, then the center of a group G acts by a character, and this character is called the central character of a representation. Final remark about this general situation. So smoothness is preserved by surjective morphism, by the operation of taking sub-representation, sub-quotient, or direct limits, direct sum, sorry. So one thing which will be very important for us is when we have a group to construct representation, and a way to construct representation is to take a subgroup of a group and assume that you already know a representation of that subgroup and then induce them, so build representation of the bigger group by using representation of smaller groups, of subgroups of a group. So the first notion is what we call smooth induction. So we'll start with a subgroup H of G, which is assumed to be a closed subgroup, and with a representation tau W, smooth representation of H, then you can induce that representation, and the space of this induced representation is the space of function from G to the with value in W. We satisfied the property that are written here. So f of Hg is tau of H Fg for when H is an element in the subgroup H, and moreover that exists. And when you start with we have a function f, we can attach to it an open compact subgroup K sub f, such that for all the elements K in Kf, the function satisfies the following condition. So f of gk is equal to f of g. So this space is stable under the action of g by right translation, and the representation we get, which we denoted by in h of tau, is called the smooth induced representation of tau. So this is the most general situation, but we can have another way of induction of inducing. So we can consider the subspace of this representation in H of W, subspace formed by the function with compact support modulo H, and this subspace is still stable by the action of G and provides a sub-representation of a previous one, which is called the compactly induced representation of tau. And of course, in the case where the quotient space G mod H is compact, then these two representations coincide. So we will see that this representation will have different interests. So until now, I was just looking at locally profiled group, but for reductive group, we have also all the machinery coming from the structure of a reductive group that we have seen already in the case of Rioli groups. And so in that case, you can say more. So first, I want to put some state some notation. So first we have defined a parabolic subgroup of G, P, which is, so it's an algebraic subgroup which contains a Borel subgroup. You already know by U is unipotent radical. And if P is, so this is P, blackboard P, so this is at the level of algebraic group. But if the parabolic is defined over our p-adic field F, then we will call it an F parabolic subgroup. And so P, of course, has a Levy component subgroup L. And so we can define it as, so if you assume that P is defined over F, then Levy is defined over F, and it is such that the map which send L, U, L an element in L and U an element in U. You send it, this map, we send LU to the product of L and U, defines an F isomorphism of algebraic variety between L cross U and P. And such sub always exists and is connected. And you will need the following subgroup of L, so which I will generally denote it by A or sometimes A sub L if I need to fit to precise to which Levy it is attached. And this group is a maximal F split torus lying in the center of L. It is possible to show that A is unique and that A is unique and L is the centralizer of A in G. And we call this group A will be called the split component of L. So now we can consider the F rational point of all of this group, P, U, and L, and A also. And then we have a Levy decomposition of P as usual. So L is isomorphic to the quotient of P mod U. And the group P, which we call a parabolic subgroup of G, is a closed subgroup of P. And so you can induce, and the quotient of G mod P is of G by P is compact, and you can induce representation from P to G as we have defined before. And in this case, there is no difference, as I've already said, between smooth induction and compact induction. So we'll give two examples. First one would be GLN. So GLN, I have already said remark about the maximal compact subgroup of GLN. And up to conjugacy, a parabolic subgroup of GLN F is a subgroup of upper block triangular matrices. The unipotent radical of P is formed by the matrices which has their diagonal blocks as identity matrices, and L is a subgroup given by the block diagonal matrices. So L is a product. The nice things here is that L is a product of smaller group of the same form. So GLN I over F with the sum of the Ni equal to N. The second example which will interest us is the case of SL2. So 2 by 2 matrices with coefficient in F and determinant equal to 1. So the torus, we can consider torus in that case, so SL2 is small, so we have only two kind of parabolic subgroup, the group G itself or a Borel subgroup. And in that case, the levy is a torus shape, and the unipotent radical of the Borel is written here. And we have also this group, which is the unipotent radical of the opposite Borel subgroup. Okay. And if you take any character of a torus T, you can extend it trivially to a character of B by just setting that chi of T U is just equal to chi of T, where T is in T and U is in the unipotent radical of B. And the fact that U is normal in B implies that this character chi, this extended character chi B, it should be chi B, is well defined. So this is a very special case of the following situation, which
Sorry,
is
Marie, can I ask a question?
yes.
What is the group B in the SL2 example? The Borel?
B is T times U.
T, okay, thank you.
Yeah. And so it's a block diagonal matrices, invertible, and with determinant 1. So now we will generalize this situation of a definition of this character chi B for an arbitrary parabolic subgroup of a reductive p-adic group in two ways. So first, we have the notion of inflation of a representation from the levy to P. So you start with P a parabolic, L a levy subgroup, and you can, if you have a representation, you start with a representation sigma of a levy, and then you extend it as a representation of P, which is trivial on U, and then it will be denoted by inflation from L to P. And so we get the representation of P, and then you can use the functor that I have previously defined of a smooth induction from P to G. And the composition of these two functors, so you go first, you start, so R of L, so I should have defined this. R of L is the category of smooth representation of L. You take a representation in L, you inflate it into a representation on P of P, and then you smooth induce that representation, and you get a representation of G. And okay, so and doing that, you get a functor from the representation of L to representation of G. This functor admits the left adjoint, which is obtained in the following way. So first, we start with representation in G, and you use the just the restriction. Okay, it should be. Yes. Okay, there's something wrong here. It's the restriction from P to G, and you get a representation of G of P. Then you take the U co-invariant. So it was what. So you define V of U, the set of elements of the following form pi U V minus V, where U is in U. So this is a representation, a space which is stable, which is stable by L, and so this defines a representation of L when you start with P. So this composition defines a functor from the category of representation of G to the category of representation of L, and it is the left adjoint of a parabolic induction functor. These functors are both exact. Okay. So kind of repetition here. So this can be proven quite easily, but it is interesting to see if what we can say about the right adjoint of this parabolic induction functor ILPG. And it occurs that it is the parabolic restriction functor, but with respect to P bar, where P bar is the opposite parabolic subgroup of P. By opposite parabolic subgroup, it's a parabolic subgroup which has the same Levy subgroup, but opposite unipotent radical. For example, in the case of SL2 or GLN, if you take parabolic subgroup which are we have 0 on the under the diagonal, then the opposite will be just the other way, so with 0 up the diagonal. So this is due to Bernstein and its most involved result. And in particular, it shows you something. It's why I was very cautious to write RLP, because the parabolic restriction depends on the choice of P in general. So now we can use this induction in the special case where P is a Borel subgroup, and we can consider all the irreducible representation of G which are subquotient of the parabolically induced representation from the Borel of a character of a torus of B. And this set of representation is called the principal series representation, principal series of representation of G. So we will see in examples. So in some cases, this induced representation is irreducible. For example, for SL2, we have cases where it is irreducible, and other cases where it is the sum of length to direct sum of two irreducible representations. So we'll come to the example later. Then we can, at the opposite, we can also consider another kind of representation. So this kind of representation will be important for us, and here it is a difference from the situation for real Lie groups. So representation which has the property that the parabolic restriction functor of pi is equal to 0 for any proper parabolic subgroup of G is called supercuspidal. Because using the adjunction of two functor induction and restriction, it is easy to see that an irreducible representation it is clear that an irreducible representation is supercuspidal if and only if it does not occur as a subquotient. I mean, it does not occur as a quotient of a proper parabolically induced representation. And then we can also show that it is equivalent to say that it is not a subquotient of a proper parabolically induced representation. Okay, so this is a definition and the first description of supercuspidal representation, but there is another way to characterize this representation, and it is done using the following concept, which is that of matrix coefficient that we have already seen in the case of real Lie groups in a picture lecture. So a complex function on G is, which has the following form. You start with an element in G, so you fixed an element V tilde in the contragradient of V. So we have a representation. So it is attached to a representation by V, and so you fix pi tilde V tilde, sorry, an element in the contragradient of a vector space of a contragradient of pi, and V an element in the vector space of pi, and then you attach to it the product of V tilde, so the evaluation of V tilde over pi G of V. So we call this, this is called a matrix coefficient of a representation pi, and we have the following result: an irreducible representation of G is supercuspidal if and only if all its matrix coefficients have compact support modulo the center of G. And actually, it is equivalent. It is also equivalent to say that that there is one matrix coefficient which have compact support modulo the center. So maybe it's time to give you some example of supercuspidal representation. So first, I mean, it's not exactly an example, but it's a description. So any supercuspidal irreducible representation of SL2F can be induced irreducibly from an open compact subgroup of SL2. So this result is so in the case of when you take for F of a finite extension of QP and P is not equal to 2, then this is due to Charlicka. So it is in fact true in general for with no condition on F for any, in fact, any non-Archimedean local field, and also for SLN over F. In that case, it's due to Bushnell and Cusco. And this is a very general result, which is expected to hold for any p-adic reductive group. And at the moment, it is known for any classical group if P is odd, and it's due to, so for GLN and SLN is Bushnell-Putzko, and for other classical groups is Sean-Stevens. And when G is arbitrary, so you can take, for instance, a group of exceptional types, there is a construction due to JKU, which constructs supercuspidal representation as in this way. So we show that any supercuspidal irreducible representation of G is induced from an open compact subgroup. And it's give all the, in the case where, so it's G is not arbitrary, G has to be, but in our case, I assume that G is split, so it's okay. So, and in fact, it's for a group which split over a tably ramified extension. And it's true if P is not too small, and the condition is that P does not divide, okay, it is clearly wrong, what I said. It does not divide the order, so P is large enough. So P does not divide the order of the Weil group of G. And okay, so it means that induction, but compact induction is also very useful, even for representation which are supercuspidals, which are not captured by parabolic induction. Okay, we'll come back to this later. So first, give some more results regarding SL2. So our p-adic field F has 3 quadratic extensions, which are of the following form. So F square root of A, where A is epsilon pi or epsilon pi, and of course, epsilon and pi are elements which are not in F. And I mean, more precisely, there are elements that their square, their root square is not in F. And the one attached to epsilon is the one is unramified, and we call it this one for epsilon, and the other two are ramified. And also we will need the following definition. When we fix a non-square element A in F rows, and then you attach to its side the following character. So sine A of X is equal to 1 in the case where the element is given by belongs to the image of a norm for the corresponding field extension, and -1 otherwise. And so for each extension, that extension, we can construct a supercuspidal representation, a family of supercuspidal representation of SL2F. And each family itself can be parameterized by a non-additive character of F and a non-trivial character of a kernel of a norm map. And when P is odd, it gives all the supercuspidal. When P is equal to 2, there are more, but I will not enter in this in this specification. So why are supercuspidal important? Is for the following reason, because we are in some sense a building block of the other irreducible smooth representation. So it's a theorem which is due to Harishchandra. We said that any smooth irreducible representation occurs as an irreducible component of a parabolically induced representation from okay, my notation. Okay, from a supercuspidal representation of a Levy factor. So when I said parabolically induced representation, I mean the factor of parabolic induction that I have defined before. And okay, so we have supercuspidal representation, but one question is, do you have other representation which are more related to what we have for real groups, and which occurs to be the notion of square integrable modulo the center representation. So it is an irreducible representation such that the restriction to the center of a group is a unitary character, and that the complex absolute value of every matrix coefficient of pi belongs to L2 of G mod Z. So the condition is written here. So in terms of the matrix coefficient previously defined for representation. So we have seen that, yes?
I have this naive confusion. In the previous Harishchandra result, it says everything comes from a parabolic induction with some Levy factor becomes supercuspidal. But didn't we say that the supercuspidal representations are not parabolically induced? They don't.
No, supercuspidal are not parabolically induced.
But here it says any smooth reducible representation has to come from parabolic induction.
Yes, but but for parabolic, when I define supercuspidal, I say that it's not parabolically induced. Maybe I should, maybe I didn't say, for a proper parabolic subgroup.
Oh, I see. You can take the whole. Okay.
Yeah.
I see. Okay. Thank you.
Okay, I think this is a difference from real group, because I think in real case we do not have something equivalent, similar notion as a supercuspidal representation. So until now I was using, so okay, just one thing. Now we can. So until now I did not fix the parabolically attached to Levy. So, but if you fix a maximal torus T in G and be a Borel subgroup, and you consider all the Levy subgroup which contain this T and parabolic subgroup which contain the Borel B, then they are in bijection with the subset of a root system of a group attached to this choice of a Borel and a torus. And so in that case, I would simply denote the induction by ILIG, and also I will as defined in Peter's lecture, we have a notion of modulus character and also of a unimodular group. So a reductive p-adic group is unimodular, but the parabolic are not. And so we have, so you can modify the parabolic induction by including the module at the power 1/2 and the module of a unipotent radical of P. And in that case, you get an induction which is called normalized parabolic induction. And with this, so this would be for the normalized version of this induction, normalized version. And then when you do that, you can consider okay, first thing, when you have a representation of p-adic group, they are not necessarily semi-simple, but you can look at the Grothendieck group of a category of representation of smooth representation of G, which means that essentially that you would take the semi-simplified form of your representation, and you can consider the induction and restriction functor also in this the corresponding functor in the corresponding map operator in the Grothendieck group. And you can consider this the following alternated sum of parabolic restriction composed by parabolic induction, normalized one. Then it is possible to check that this operator is an involution and preserve irreducibility up to psi, which means that when you start with an irreducible representation, its image by dg is plus or minus 1, an irreducible representation. And by definition, if you start with a supercuspidal representation, all the parabolic restriction will be equal to 0, and except the one which corresponds to the Levy, which is G itself. So if a representation is supercuspidal, dg of pi is pi up to a sign, we can be here if pi supercuspidal. Okay, so for supercuspidal, this involution has essentially no interest, but you can take another representation. You can apply this involution to the trivial representation of a group. So in that case, the parabolic restriction of a trivial representation, if you think of it, it's just a trivial representation of a Levy subgroup. And so this parabolic restriction in that case just disappear, and you get the image by dg of a trivial representation of G is the alternated sum of -1 at some power, parabolically induced representation, normalized parabolic induced representation of a trivial. So it is by this result and by the preservation of irreducibility, it is irreducible. And it is possible to check that it is in the discrete series of a group. So it is an example of a square integrable modular center representation. And in particular, this is a difference from the real groups because we always have discrete series. So now in the last part of a talk, I will give some result about harmonic analysis on p-adic reductive group. So the first things will be the following definition. So we start with a smooth representation of G and a function locally compact with compact support function f on G, and then you can define an operator on the space of a representation by the following integral way. And of course, similarly, we have an, okay, I forgot to say that we can, when you have a PID group, it always admits a left arm measure, and it is unimodular, so the left arm measure coincides with right arm measure. So but we have to fix one. And so this operator is useful to understand the link with admissibility. So when we start with a smooth representation, it is admissible if, so we have already seen that if the starting representation is irreducible, there is no difference, so it is always admissible. But for non-necessarily irreducible representation, then it is admissible if and only if pi of S has finite rank. And so this is useful because in that case, you can define a linear functional on the set of function over G, which plays the role of a character in the case of a finite dimensional representation of a finite group. So one thing that I didn't say, that I should have said, so periodic field is a local field. So in many aspects, he shares feature with real Lie groups, but it also has a finite reductive, finite residue field. So for that reason, it also shares some property of a finite group. And actually, the definition that I gave about for this in the involution, which was just before, the definition for the involution is in fact just an imitation of a Curtis involution for finite groups, finite reductive groups. And here we also have a notion of character. So we start with an admissible representation, then its character, which is a definition is due to Harishchandra, is defined first as a distribution on G, which is the trace of that operator pi of F. And Harishchandra proved that in fact there exists a function. So the distribution will be capital theta and function small theta, theta pi, we value from G to C, which has a property that you can write the distribution using that function. And this function is a class function, which means it is stable by G conjugation. So this will be very useful also in the applications. And we can, and we will see a property right now. So we have a notion of veil discriminant function, which is same as for real group, and an element is called regular if the value of a veil discriminant is non-zero on it. And we will denote by G-reg a set of regular elements in G. It is a dense subset of G. For SL2, we can compute explicitly the veil discriminant. And okay, so this is a remark because usually the usual definition for the character of a for function theta pi attached to the character of a representation is usually a function defined as a function on the regular set G-reg. But because it is an open subset, we can just take the function which is zero outside that set. And my last result that I will state now is we can consider the Lie algebra of G, and we can fix symmetric non-degenerate bilinear form on G, which is G invariant. And with this form, you can define, as we have seen for real group, the Fourier transform, which is defined similarly. And now if you consider an orbit in G under the adjoint action of G on this Lie algebra, then this orbit has an gene variant measure on it, and you can define the Fourier transform of that measure as the value of the measure on the Fourier transform of F. And the result of Harishchandra is that, in fact, this distribution mu at O is represented again, also by a locally integrable function on G. And that function is locally constant on the regular element in the Lie algebra. And if you multiply it by the half of the absolute value of the discriminant, y discriminant on the Lie algebra, you get a function which is locally bounded. Okay. And just an example for SL2, of course, the form we can take, usually take would be just a trace of X, Y, and the y discriminant on the Lie algebra is as the following, is computed as follows. And every nilpotent orbit in SL2 in the Lie algebra of SL2F is a conjugate of one of the elements of the following form. So 0A, so in upper triangular matrices, 0A, 0, 0, where A is 0, 1, or one of these three elements, epsilon, pi epsilon, which are attached to the extension that we have seen before. So this is what I will say for today. So for tomorrow, I will essentially concentrate the talk to tempered representation. So tempered representation, which are generalization of discrete series, and I will try to explain how the reduced C-star algebra of G would play a role in the understanding of tempered representation. And the third talk will be to mix, in some sense, smooth representation and tempered representation. Okay, thank you very much for your attention.
Thank you, Anne-Marie. All right, so questions and comments. There is one lingering. So there was a question about if we compose the induction and restriction functors, do we get an intertwining operator on the original L representation?
So could you repeat your question? Sorry.
Is the composition of induction and restriction an intertwining operator?
No, I don't think so. I mean, intertwining operator will play a role tomorrow, but this is just this is not because you go from one group to the Levy. You mean induction and restriction, like in the involution?
Yeah, I guess naively you start from an L representation, go all the way to G, and then restrict all the way down back to L. Do you get an intertwining operator on the original representation that you started with? Kind of. I think that's the question.
Okay, it's just okay. I did. Okay, I will think of it. I don't know.
All right. Okay, and then there was one question, I guess, but the person asked the question was about admissibility, whether the hypothesis on G was enough to exclude, for example, discrete groups. But the person asked the question left already. He had time restrictions. So there was one interesting thing that came up about this supercuspidals and the
Yes.
analog in the real setup.
Yes.
Roger made the suggestion that perhaps because their matrix coefficients are compactly supported, they're like integrable in a strong sense. Maybe Roger has the idea that maybe L1 integrable representation, integrable modular center in the real setup could be corresponding to supercuspidal in the p-adic.
Yes, this is interesting. Yeah.
Yeah, so I was gonna ask. So, I guess that's the thing, right? So in L1, integrable representations give you isolated points in the felt topology. So
Yes.
these supercuspidals also sit isolatedly then, since
Yes.
compact.
Yes.
Yes. Yeah.
Yes.
Are they the only isolated ones in the duo, or are there more isolated points?
Well, the point is, of course, the supercuspidals do not exhaust the discrete series, so there are always going to be more isolated points. So I need to know from the experts in Lie groups. For SL2R, for example, in the discrete series, how many of those elements in the discrete series are L1, are integrable as opposed to square integrable?
I think only the first one, except almost all one except the first one, because the first ones sit in the limit of complementary series, so they are not isolated in the full unitary dual. They're isolated only in the tempered dual, the first pair of dots in the discrete.
So it seems to me there's a chance that supercuspidal representations may have an analog for Lie groups, and it may be the integral representations, but I need more expertise from people in Lie groups to develop this idea.
Well, I'm afraid I cannot help much. I'm trying to remember if the integrable representations are known for real groups in any concrete manner, and I seem not to have run across anything.
Yeah.
There's a condition on the infinitesimal character in terms of the roots that tell you if it's L1 or not. And I was trying to look it up, but I can't immediately find it at the moment.
Oh, thanks very much, Peter.
Thank you very much. It's interesting.
Find it, I'll send it.
I thought, so in the construction of discrete series, Peter used the full, to get the discrete series, you basically use the G as the parabolic, right?
Yeah, so there's no induction.
Yeah,
no induction.
here it was also similar, that supercuspidals, they cannot come from proper parabolics. So that there seemed to be kind of a similarity there, but is it only because it was SL2 for higher rank groups? Do you have to use can you get discrete series from parabolics in the real case? I guess asking Peter, since he did the real.
Sorry, what was your question?
In the real case, to get discrete series, can you get discrete series from proper parabolics in general?
No, so only the limits of the discrete series can occur inside induced representation from parabolics.
That's not true discrete, right? Okay, so in that sense, there seems to be an analogy here, right? Discrete series and both supercuspidals, they don't come from proper parabolic induction. They at the really G level, they're not endoscopic or whatever, I'm throwing these big words there, but yeah, so they're genuine, they're not coming from smaller groups inside somehow. Interesting.
But the point is that for p-adic, we have discrete series we came from parabolic.
But not from proper parabolic, you said?
Yes, not for supercuspidal, but we have discrete series that are not supercuspidal.
Yeah.
Like the standard, for instance, which is in the principal series.
Mm-hmm.
But yeah. But maybe we do not, maybe it's this one that we do not have in real. Oh, do you have some representation which displays the whole of a Steinberg representation?
I think at the for SL2R, if at the tip of the complementary series, there's a representation of length 2, and one of its subquotients is the trivial representation, and the other subquotient is another representation, which
Yes.
seems to me like a Steinberg representation.
Yes. Yeah. Yes.
Oh, by the way, there is a question. At which moment was the F-split hypothesis used? Did you use the hypothesis today?
Okay, it was not used. It was the hypothesis. What was used was quasi-split, in the sense that I assume to have a Borel. At some point, I take Borel subgroup, which is. But if we just replace a Borel subgroup by a minimal parabolic subgroup, then it works for any reductive group.
Can I ask a bit of a basic question? It seemed like there was no topology assumed in any of the representation spaces. Is that correct, that in the p-adic case you don't need any kind of topology and you don't talk about unitary representations, for example?
Yes.
So
You mean? Yeah.
And the dual representation was really the literal space of all linear maps.
Yes, the dual is for all the linear. Yeah.
Okay. Yes.
Oh, I didn't catch that.
Well, could I just clarify that? Of course, you have the smooth dual, which is what Anne-Marie has been talking about today, but you also have the tempered dual, and that admits a failed topology.
Yes.
A risky topology, exactly the same as the real case. Yes.
Yes. Yeah. The tempered world would be more similar with real situation. Yeah.
In terms of computing the C-star algebra, group C-star algebra, I see that Roger computed, I think, as a paper on the p-adic GLN 87. This was this before or after Wasserman announced the real?
Before.
So
before.
It seems. Why is it? Is it the representation theory is easier somehow? What makes it more?
That's the thing about the general linear group, of course, the general linear group. And yes, it does have certain features which make it more straightforward. To be more precise, the representations induced from the discrete series are always irreducible. So all the R groups are trivial. So in that sense, it's more straightforward. It didn't seem straightforward at the time, but in retrospect, it's more.
Sorry, I didn't mean it that way. Yeah. I see. So I'm guessing that your paper has the details.
It does indeed have the details.
All right. Any other questions or comments?
I just like to link today's talk with yesterday's talk. If you take the limit of discrete series representations for SL2R, so these are two irreducible representations at the tip of the non-spherical principal series, then we know what their Harish-Chandra characters are by Anne-Marie's talk. I'm talking about the little thetas. Now, if you take those two elements in the limit of discrete series and take the sum of the characters, that sum is identically 0 on the maximal compact of SL2R. You'd expect that because they lie in the principal series. But if you take them separately, the characters θ1 and θ2 are not identically 0 on K. So they have that in common with the discrete series. So that is probably quite a good reason for calling them limit of discrete series, because their characters separately behave like the characters in the discrete series. Yeah.
Thank you. Well, let's thank our speaker again. Thank you, Anne-Marie, and thank you, Han, today. Going to continue tomorrow, so I'm going to stop the recording now.